Luis, creo que tenemos que expresar un especial agradecimiento al ingeniero Rubén Massaro por esta participación que ha tenido en la primera jornada nacional e internacional de adyuvantes para herbicidas. Y se viene la segunda conferencia así presentada.
Estamos sembrando la agricultura que vos y el mundo necesitan para que los cultivos se transformen en más y mejores alimentos. Desarrollamos tecnologías microbiológicas que estimulan el crecimiento y así podemos nutrir al campo y al mundo pensando en hoy y en el mañana. Rizobacter, mejor agricultura.
Seguidamente, la primera conferencia de un disertante internacional. El título es 3 reglas para una mejor eficacia con adyuvantes organosiliconados, a cargo del doctor Policcelo de la empresa Momentive de Estados Unidos.
Hi, I'm George Policcelo. I'm a research fellow with Momentive Performance Materials. I've been involved in the development of the organosilicone super spreaders for the last 38 years, and I'd like to talk to you this morning. Farmers have been using adjuvants for many years, but organosilicone adjuvants have been actually used for the last 30 years or more. And these products, although they're used all around the world for such a long time, many people still do not take full advantage of how these products work. So what I'd like to talk to you about today is looking at some 3 basic rules, 3 basic concepts of how we can use organosilicone surfactants as adjuvants and increase our efficacy and get better performance. How do we maximize the performance from these products? So in general, farmers need to optimize the use of resources such as land and water and labor, and they need to do this in a sustainable way. The problem is, how is that possible? Because we're taking all of these things together and we need to be able to maximize and optimize the performance of these attributes so that the farmer gets the biggest return on his investment. And again, do it sustainably. So how is that possible? Well, one solution is to use a high quality organosilicone adjuvant, in this case, Silhouette super spreaders. These are products that allow us to reduce the contact angle of water almost to a thin film, and we're going to see that we have some very, very unique properties and some great advantages from these types of products. But let's just look at the word adjuvant, because adjuvant comes from the Latin word adjuvare, and this word means to offer help. So that's the whole purpose of an adjuvant. It's to help the grower use his spray mixture in a way that gets more out of it than he would without it. And so adjuvants are used to enhance the performance of agrochemical sprays. They allow us to get spray to the target, because that's the important part. We want to get the spray from the spray nozzle to the target. It'll improve our deposition. It gives us better coverage, and adjuvants can help us increase penetration of our crop protection product into the leaf through the cuticle and help us to get the type of performance we're looking for. So I want to look at 3 basic rules, 3 concepts that can help us use organosilicone adjuvants to their fullest. And so these 3 points are 1, adhesion, 2, spreading, and 3, penetration. So if we look at adhesion, we're talking about a droplet comes from the nozzle, lands on the leaf. Does it stick or does it bounce off? And in this case, we're looking at improving the deposition, because if we get more droplets sticking to the leaf, I'm getting better deposition. And the important thing here is, if my spray is sticking to the leaf and not bouncing off, it means I have fewer kilograms of product on the ground. When I spray, I want my application to stay on the leaf. I don't want it bouncing all over the place, because then it's not doing its job if it's on the ground. Once the droplet is on the leaf, then we go to the next step in this process, and that's spreading. And in the case of organosilicones, we get super spreading, and we'll talk about that in a little bit, but we can see this high level of spreading on this leaf. We get improved coverage, we get better distribution of the active ingredient across the leaf, and in the case of insecticides or even fungicides, This can help get the spray to those little nooks and crannies where the insect is hiding and you wouldn't get with a normal spray. The third rule or third attribute here is penetration. Silicones have the unique ability of infiltrating stomata, and we will talk about that when we get to section 3 of this talk. By infiltrating stomata, we get the chemical into the leaf very, very quickly, within minutes, seconds even, and that makes it resistant to wash off. So if we are taking advantage of the infiltration process, once we get the material into the leaf, if it rains, we're not going to have a loss of the active ingredient because it's all inside the leaf, and we'll show you that. In addition to stomatal infiltration going through the stomata, we also get penetration through the cuticle. So that waxy layer that's on the surface of a leaf, your droplet sits on that surface, and over time you get passive diffusion of that application through the leaf, in allowing it to be distributed throughout the plant. And that is also helped by the using an organosilicone adjuvant. So we get great penetration when we do that. The whole point is we need to get the treatment where it needs to be. We need to get it to stick to the leaf. We need to distribute across the surface. And in cases where we need penetration, we need to get it into the leaf. So let's look at the first rule, the first property here is droplet adhesion. As I said, when we spray an application, we want the droplets to stay on the leaf. We don't want them to bounce off. So we're going to look for improved deposition, and as I mentioned before, this leads to fewer kilos of our crop protection product on the ground, keeping it on the plant. Well, one of the main factors in droplet adhesion is dynamic surface tension. We might ask, what is dynamic surface tension? When your spray is formed at the nozzle, as it forms a sheet or the cone and it starts to break up into little droplets, at that time when the liquid leaves the nozzle, the surface tension of that spray is very close to that of water. But as that droplet falls through space towards the leaf, the surface tension is getting lower and lower with time. Now this whole process takes somewhere between 75 and 100 milliseconds. So it's a very short period of time, but surface tension needs to decrease from the surface tension of water down to a critical surface tension that will allow it to wet the leaf. And that's dynamic. It's surface tension versus time. Very, very important in this whole process. So we need to get the surface tension from the surface tension of water when the droplet is created to a low enough surface tension so that it sticks to the leaf. And so in this illustration here, we see a droplet coming down from the nozzle. As it approaches the leaf on impaction, that droplet may be moving very fast depending on its size and speed. If the surface tension is not low enough, when that droplet impacts the surface, it's going to expand, it's going to recoil, and the droplet's going to bounce off, and I lose material. And I'm wasting my agrochemical because it's going on the ground. However, there's another place we lose chemical, is if that droplet is falling and the surface tension is still very high. When that droplet hits the leaf, it doesn't even expand, it just shatters, and the droplets roll all off the leaf, and we lose active ingredient that way. But the optimal situation is when that droplet approaches the surface tension has sufficiently reduced to a critical level where the droplet hits, it expands, it recoils, and it sticks. And this is all a function of dynamic surface tension. So if we look at on this axis here, this is adhesion, the percentage of the droplets that actually stick to the leaf versus the surface tension at 100 milliseconds. So it's at that time from when the droplet is formed till it comes to the surface of the leaf. So here we have surface tension. At a high surface tension, if we get close to 55, I'm not getting very many droplets sticking to the leaf at all. And we did this using a droplet generator, forming droplets of a known size, allowing them to fall a given distance so we can measure everything, and we can determine that if my dynamic surface tension is relatively high, at impaction, most of my droplets are going to bounce off. I'm getting about 10% adhesion. However, if I can get that dynamic surface tension down to around 45 millinewtons per meter or less at 100 milliseconds, then I start to get some significant adhesion. And as I get down to about 30, 36 or 37 or 40, you can see I get very high adhesion on the leaf. My droplets are sticking. Please don't confuse this with equilibrium surface tension. Most of us measure static surface tension. When we say, what's the surface tension of the fluid? This is where they take a solution, they put a probe in, and they measure the surface tension after a few minutes, and that's the surface tension. That is equilibrium surface tension. That does not get us this dynamic effect. We're looking at surface tension at a very short time frame. If we don't have the right surface tension there, droplets don't stick, as you can see here in this diagram. So here, let's look at an example. Whoops. You'll see here's a droplet of water falling on this leaf, and it hits and it shatters into many, many droplets and just blows off the leaf. And I'm not maintaining anything. That droplet, again, here we see the same example. It just goes off the leaf. I've lost 98% of my application. If I use an organosilicone adjuvant, you can see that droplet fall and it just sticks to the leaf. Nothing bounces off. Let's watch it again. The droplet comes down, it hits the surface, because the dynamic surface tension on impaction is such that the droplet now has a low enough surface tension that when it hits that surface, it can expand, but it stays. We get adhesion to the leaf. If we don't accomplish that part of the 3 rules, we are not getting the maximum performance out of our product. Once the droplet is on the leaf, then we get to spreading. And in the case of the organosilicones, it's super spreading. And there's some really great advantages of having a super spreader, because if you think of this leaf here that's got this liquid spread out over it with some dye, if I have just droplets of water, you saw them on the previous slide, and even here little droplets beaded up on the surface, I'm not getting great coverage. If I can spread my liquid out, that means I have the potential of reducing my water volume, which means I can spray more hectares per tank. So if I'm spraying 400 liters per hectare on potatoes, I can take that down to 100 liters per hectare. So if I have a 400 liter spray tank, I can spray 1 hectare. But if I have a silicone in the solution to give me the super spreading, once I get out to the field, I can spray 4 hectares with the same tank. So it increases my efficiency and productivity significantly because I'm not using as much water. And quite often we can reduce the amount of water. So let's look at the spreading properties. The performance of the organosilicone super spreaders, and we call them super spreaders because that's exactly what they are. They spread better than anything else. If you look here in the red bars, as we increase the concentration of the red, this is your conventional adjuvant, non-ionic surfactant. I can go from 0.025% up to 0.1%, and it doesn't matter. I can go to 1% and my spreading will not get any better than this. That's the maximum a traditional surfactant can give you. However, if I use the organosilicone, I get 3 or 4 times more spreading even at the low concentration. And then as I increase the concentration, I get massive amounts of spreading. If you look here, this is a polystyrene petri dish, a very hard to wet surface, contains 0.25% droplet of the conventional adjuvant. You can see it doesn't really spread very much. On the other hand, the organosilicone at 2.5 times less, so 0.1%, you can see these little black lines around the outside. That's where this dye is spread out. In fact, if we look at it, that's the area that's covered by this surfactant. Let's take a quick look here. On the left is a drop of water placed on this polystyrene petri dish, and you can see that it is not spreading very much at all. On the right, we're using an organosilicone. We put it down, and if you look, you can see that that droplet is starting to spread and is spreading very rapidly, and it's going to cover a much, much larger area. And the key is they're both the same volume. This is such a thin film on the right that I'm able to push this droplet out. So think about it. How many droplets this size on the left do I need to cover the area on the right? Pretty close to 100. So that gives you an idea of how much we can reduce water requirements when we're spraying high volumes. What do I mean by high volume? If we're spraying to runoff, we can at least take that spray to runoff application and cut it in half very, very easily. So let's take a look at a spray application here. On the left is your conventional adjuvant, on your right is your organosilicone. And if you look, I still have very discrete droplets on the left, and on the right, you can see that my droplets have now spread out. I've got a nice shiny leaf because I'm getting complete coverage on that surface. I have better spreading with the organosilicone than I get using just your standard everyday adjuvant. These are things that your typical adjuvant cannot accomplish. So what's one of the benefits now? Remember, we talked about being able to reduce spray volume. So let's look here in the upper right-hand corner. I have two factors that are going to be addressed in this next chart. I have adhesion. So we're going to take advantage of the droplets sticking to the leaf. Once they stick, they're going to spread, and as a result, I can use less water. Let's look. Here I have 2,000 liters per hectare. We're looking at the effect of droplet adhesion on apple. This is Cox's orange pippin apple, some work we did down in New Zealand. Looking at calcium uptake into the apples, looking at fresh weight, we can see that at 2,000 liters per hectare with the calcium application alone, I'm getting about 2.2 milligrams per 100 grams of fruit. If I add 0.05% of an organosilicone, I'm pretty close to doubling that amount. I'm doubling the amount of material I'm getting into the plant at 2,000 liters per hectare. So what everyone would say is, hey, if some is good, more is better. If we increase this organosilicone to 0.1, now I'm really increasing the spreading a whole lot. Look what happens. I've lost my uptake. Why? Because I'm getting runoff. Silicone spreads so very well. One of the take-home messages I'd like you to take away from this talk is that we always want to look at our spray volume. We always want to look at our spray volume and make sure that we're not running things off the plant. So if I take that spray volume and cut it in half, look what happens. 0.1%, getting a high level of spreading, but my spray volume is 50% less. I maintain the material on the plant, I'm not running anything off, and I get my efficacy back. And the benefit here is I'm getting, using less water makes it more efficient. I can spray more hectares with the same tank than I can if I'm spraying with the traditional adjuvant. So a big advantage. Let's look at the third and final rule that we want to take advantage of, and that's penetration. Penetration occurs two ways. We can have stomatal infiltration or cuticular penetration. Cuticular penetration is the droplet sits on the surface of the leaf, and over time you get passive diffusion through that solution, through the waxy cuticle into the leaf, and it moves it around the plant. But that takes 1, 2, 10, 12 hours, sometimes 24 hours to get sufficient uptake. Organosilicones have the unique ability to flood stomata. So if you look here on the right, here is a photograph of a leaf surface. It's a Viscifaba, so it's bean leaf, and you can see the stomata are all lit up because in this case, the silicone surfactant has flooded those stomates and pushed the dye inside the leaf, and you can see everything that's lit up is under the surface of the leaf. It's in the leaf and it happens very quickly. So let's look at an example. Here we have on the left your conventional adjuvant again. It doesn't spread very much. The one on the right is spreading, so similar to the previous example. So these are radish leaf. And now if we take them 2 minutes after application and wash them, look what happens. On the left, I've lost all of my application. It just washes off. This is where the dye was, so keep an eye on that spot. And then here, you can see the silicone has spread off, spread out. I'm not washing hardly anything off. Most of my application is retained. It's inside the leaf. So if it rains, the application is safe. So let's look at a herbicide example. Here we did some sprays in Malaysia in a palm plantation. We're looking at the effect of glyphosate on mixed weeds, and we're going to look at the effect of adhesion, the effect of spreading, and the effect of penetration, getting the material into the plant. The standard application is Roundup at 450 liters per hectare, and you can see in the yellow bars that I'm not getting very good control at all. I'm just suppressing those weeds. But if I add the organosilicone in the blue bars, you can see that even after 7 days, I'm getting a significant improvement. And out of 30 days, I have a very good control of this application. But keep in mind that the organosilicone is at 50 liters per hectare. So I have improved performance even at 90% less water in this case. So going from a high spray to runoff at 450 liters per hectare to 50 liters, I'm taking advantage of the adhesion because the droplets stick. They spread out and give me good coverage on the weeds. And then I get very good penetration through the cuticle, through the stomata, into the plant, which delivers the effect that I want. So in summary, we want to remember the three rules, three factors that influence performance of silicones if we really want to get the full benefit. We're looking at adhesion, which gives me improved deposition. It means I get better spray coverage. We're looking at super spreading. We get that sheeting action across the leaf. It supports our ability to use a low spray volume. And I encourage you to try it out in some small areas and see the effect, because it means I can spray more hectares with the same tank. And then if I look at penetration, I'm getting improved penetration. It makes the applications more reliable. It makes for better control. I get resistance to wash off from rain when I want it. If I want stomatal infiltration, I use a slightly higher concentration of the organosilicone at 0.1% or less. I'm not going to get much infiltration, but when I need it, I use a low spray volume. I use a slightly higher concentration. I get that resistance to wash off, and it gives me improved foliar uptake through the cuticle, and I get the benefit of all these. So hopefully that gives you a better idea on how to use an organosilicone surfactant to its fullest to get the most out of that adjuvant that you possibly can by remembering the three rules of adhesion, spreading, and penetration. So muchas gracias. Thank you for allowing me to have this time with you today, and hopefully this has answered some questions about organosilicones.